My name is Terrence Markin, and I'm the Executive Director of the Graphene Council, the largest community in the world for graphene producers, researchers, application developers, and end users. We have hosted the Graphene in Healthcare and Medical Applications conference series, and the video you are about to watch is from that series. We're very excited to hear about what Paragraf is doing, especially with the sensing devices. So please go ahead. It's all yours.
Great. Well, first of all, thank you for the invitation to speak today. It's the first time, I believe, that Paragraf has spoken in a healthcare graphene conference. So it's a wonderful place to be. So thank you very much for that. So today I'll hopefully tell you a little bit about what we're doing. Hopefully we can show some differentiation here, which I think is significant. Graphene was spun out of Professor Sir Colin Humphrey's group in the Department of Material Science and Metallurgy at the University of Cambridge. Professor Humphreys is actually a specialist in gallium nitride, and it was his work in gallium nitride that really was the seed for the company, in that he was interested in developing ultra-fast electronics that combined the advantages of both gallium nitride and graphene. And in order to sort of progress that work, he engaged two of my colleagues, Dr. Simon Thomas and Ivor Guiney, who together, the three gentlemen, formed the founders of this company. And he challenged them with creating a high quality, scalable process for the manufacture of graphene. And this they achieved in 2017. And it was that achievement that led to the founding of Paragraf, and it was spun out at the very end of 2017, and we moved into our new premises here just outside Cambridge in February 2019. So we have today 65 staff, permanent staff at Cambridge. We have representation in the US and Japan, and to date we've raised 19.1 million in private equity funding. We're at the moment in the process of closing a Series B round, and we hope to make that announcement in the next few weeks, which will allow us to scale more than we currently do in the production of graphene. So in-house at the moment, we have the capability to produce in a similar way to graphene. We have a total in-house capability to fabricate both graphene and graphene devices. We have a suite of Class 1000 labs containing photolithography, thermal and e-beam evaporation, and an atomic layer deposition equipment that allows us to passivate the films and create the context necessary to produce working biosensor devices. We also, of course, have the materials test and evaluation facilities required. On the right there, you can see our brand new XPS system and a suite of wet chemistry laboratories to perform the experimentation. Our investors, private equity investors, include Draper Esprit, Amadeus Capital Partners, Parkwalk, IQ Capital, and the university itself. So what's new about Paragraf? What's different? So we've heard several times today about CVD processes, which have come on fantastically since their initial inception, but they do still have issues in terms of scalability caused by both metallic contamination and polymeric contamination. Mechanical damage is being managed very well, but these additional process steps do create additional cost in the development of a product. What's unique about our process is that leveraging previous research done at Collins Group, we have adapted a metal organic chemical vapor deposition, MOCVD system, to produce graphene on wafer in a single step. So there's no transfer process. We go straight from the gaseous phase to a single layer or multi-layer graphene over a wafer, and the systems actually can cope with very large area. They're using standard semiconductor industry compatible equipment. So it means the devices that are made in industry could equally be used and converted to produce graphene. And the substrates that we've already proven include silicon substrates, sapphire, silicon carbide, and so on. So this process, because it's a single step process and it is controlled carefully, we, in the same way that Graphene described, we measure the performance at every step in the operation when we produce biosensors. We can demonstrate that the process has zero contamination, and because it's a single process step, is therefore much more cost effective. At the moment, with our current facilities, we have 3 reactors, and that allows us, if we're working normal shifts, so a single shift and not weekends, we have a capacity already with an appropriate yield, looking at a 4x4 millimeter device of about 900,000 devices per annum. But if we worked full-time, 24/7, 365, we can produce over 3 million devices per year. So removal of copper, in particular, the copper contamination is seen as a contaminant in traditional semiconductor processes. By removing any contamination of that nature, we can start to address multiple markets and look at monolithic and heterogeneous integration with a variety of different semiconductor devices. We've actually started by marketing our own Hall sensors, which are magnetic field sensors. And these devices already, within the short period of time that we've been manufacturing them here at Paragraf, are already being tested by leading suppliers of magnetic field sensors in the world and showing comparable performance in some respects and better performance in other respects. So we're already producing devices, and we're beginning to do that in volume. We're also looking to the future. We're looking at solid state devices, including optoelectronics and high frequency transistors. And that's really where, in the long term, we see the company heading. But in the medium term, we're focusing very strongly on biosensors, and not just for diagnostics, but as we've already discussed, about gas sensing and chemical detection. So just to give you an idea of what we're doing in that respect, for anybody that isn't aware, and I'm sure most of the people on the call are aware, we are particularly focusing on graphene FETs. Graphene FETs act as a transducer. We attach a bioreceptor, which is the antibody or aptamer or single-stranded DNA, to capture the pathogen that we're looking for, or the strand of DNA that we're looking for. And when it captures that molecule, the ionic state or polar state of that molecule creates a field above the graphene channel and changes its electrical conductance. And it's that shift in Dirac point that is measured. It's a shift in voltage that we measure. And that electrical detection has huge advantages at the point of care. First of all, it's label-free. And label-free means that we can reduce the sample preparation steps. We don't have to add additional fluorophores or antibodies to create a sandwich assay. And therefore, we have reduced washing steps. And that means the instrumentation itself can be much simpler and more robust. And it means the cartridges equally are simpler and lower cost. And because we're not using dyes, there is actually a limited number of dyes that are available. And particularly when we look at point of care applications, the ability to resolve multiple dyes at the point of care with simple compact electronics limits the practical number of multiplexed assays that you can perform at the point of care. And this is not the case with electrical measurements, and we can really create a lab on a chip. Our photolithography will provide devices far smaller than is actually practicable, because actually what we want to concentrate on is the concentration of the analyte we're looking for in the volume of blood. So the manufacturing process is not limiting the size of the assay, it's actually the application that will limit it. And because we're not looking for fluorophores or dyes, we don't care about the color of the sample, so we can reduce the sample preparation in terms of, for example, whole blood. We don't need to remove the hemoglobin to get rid of the red blood cells. We can actually work with the whole blood itself. And so all of these things together mean that time to result is minimized from sample extracted from the patient through to the result. The measurements are electronic, they're made very quickly, and the sample preparation is reduced. And because the instrumentation is highly compact, robust, in fact, there was a paper published fairly recently that showed, including the wireless communications electronics, less than 6 centimeters in size. So we can see that there's a really different way of allowing high sensitivity measurements at the point of care. And that's really where we have our main interest at the moment. It's point of care applications, where the sample preparation is as simple as we might expect a lateral flow test to be, but the sensitivity is much higher, and the specificity, because of the ability to multiplex, can equally be very high. And as has been said many times before, the sample to result measurement time is very short. There's a paper on SARS done in Canada that showed 15 seconds. I think that's the world record. But depending on whether you're looking for a threshold measurement or a measurement to saturation, that measurement is typically in publications anywhere between 1 minute and 15. And of course, one of the really interesting things for the future is that we can detect both DNA or nucleic acids and perform immunoassays with antibodies and antigens. So this singular electronics platform can cover a wide variety of tests. Ultimately, the cost of reagents, if we're doing a lab on a chip, will be very low because the volumes of reagents are small, and they are actually the dominant cost in many tests today. So we're really looking at this as a technology that has the ability to disrupt point of care testing, and the applications include use at home, and the digital readout combined with smartphones that everybody has today enables that result to be communicated in a sensible manner to the person performing the test, but also in a detailed manner to the doctor that may want to review the results. So we see this as really revolutionary in future healthcare needs. So what are our goals in this sector? Well, we are looking for partnerships today. We have spent a lot of time working on the actual process and defining the process steps and the design rules for our process. And we're now ready to look for commercial partnerships to help develop novel IVD systems to help save lives. And what we can offer is not only the biosensor chip design and manufacture in-house, we have all the facilities required to do that, but we can offer high volume manufacture of high quality contamination-free graphene at a good cost point. In terms of our Series B investment, what we're looking to do is actually use a large amount of that money to increase our capacity and to make a lot of the process steps that are currently done separately integrated using cluster tools. And then, of course, we can perform biochemical functionalization, and we can also support with electronics and software development. So depending on the partnership we're looking at, we're able to offer a variety of different services, from a complete manufacture of an IVD system through to a supply of devices at scale. In terms of where we are today, we've developed an in-house platform that is shown on the right-hand side. So in a similar way to the devices shown by Graphene, we have a common gate electrode here, which is a large central square in blue. And around that, we have 4 sets of 4 different size GFETs or channels. And we've put in different size channels just to allow us to look at geometric effects and to evaluate how compact we could actually best manufacture the device. Naturally, we can make bespoke designs, and we have in-house electronics at the moment, which is combines a multiplexer, so we can read each one of the sensors consecutively. We read all 16 within a second, and that platform is readily scalable to many more channels. In terms of our functionalizing capabilities, we focus primarily at the moment on EDC NHS or EDCA sulfur NHS, which is a prevalent zero link that's used in the literature. We focus on that because it will bind both DNA and proteins, but we're also looking at the use of nanoparticles as well. And finally, just to show kind of some of the facilities we have, on the top left, we have 3 of our test cells. These are actually potentiostats you can see there that are linked by a LabVIEW program to make the continuous measurements. As I say, we poll each one of the sensors every second, and we plot those results continuously and store those results on our database. All of the processes, as I've indicated, are quality checked. So we measure the devices prior to use as a biosensor. So we understand the properties of the devices prior to and during the use. We measure the performance of the cells at each step of the functionalization process. And each one of our wafers is probed. We measure each wafer with at least 16 points and calibrate all of those points so that we have a full database of every single chip that comes out of our facility. And that's, of course, allowed us to obtain ISO 9001 certification. And we're currently working towards 13485. We don't see an immediate necessity to do that because of the time limits on attaining 13485. It is linked to the product that you're releasing, and what we're looking to do is to work with partners to release a product. So we'll do that in the fullness of time, but we're already well along the way to achieving that opportunity. So in conclusion, first of all, thank you for listening. We hope that as amplifying what has been said previously by several speakers today, graphene biosensors offer the unique ability to provide not only molecular diagnostics, but immunoassay diagnostics as well. And they provide the sensitivity of existing clinical laboratory tests with instantaneous results and the simplicity of use of lateral flow assays. So if you have an interest in working with us, please do get in contact. Thank you very much.
Andrew, thank you. Thank you for presenting on behalf of Paragraf today. I want to just ask a question, with adoption, it occurs to me that that these kind of biosensors have a lot of superior characteristics, right? They're clearly advantageous. What do you think is the major obstacle to faster adoption of this material? What seems to be the sticking point?
I think two things. One is COVID, bizarrely, in that a lot of the manufacturers have rushed to get products out the door, and there wasn't a clear end date to the COVID scenario. So people were very focused. I've been speaking to a lot of IVD companies, and they're just really busy getting product out of the door. So that has taken, I think, some of the bandwidth to developing new technologies out of the big IVD manufacturers. And the volatility of that marketplace. There are certainly here within the UK, there are companies that have won significant government contracts that then not been able to realize the full extent of those contracts. So I think COVID has had a dramatic impact on the marketplace. The second thing is obviously, as one gentleman put it to me, he said, I get a new proposition about a new technology every day. And they're all brilliant and they're all wonderful. So companies have got sort of tired of that. And they really want to see in-depth analysis of data, results, and so on. And that's what we're building towards at the moment. And the difficulty for us as a company is we want to work on contracts. We're not doing this for love. We're not doing it for research publications. So unfortunately, we're in the sort of difficult place of working with people whose results we cannot share, right. And trying to gain at the same time the attention of the big IVD manufacturers. Because for us, I think you asked the question earlier on, who's the ideal partner? The ideal partner for us is somebody who can get our technology out into the world as quickly as possible around the world. So those partners, I think, are realistic, shall I say, in that they know and understand the cost of getting a product to market, both in the regulatory approvals and then marketing and distribution. So that cost is appreciable. So they really want to see a good, robust results, including costings, before exploiting it. That would be my interpretation.
Totally understood. I think this is a conversation that's had across graphene in general. I think we're at the stage, if you look 10 years ago, the question was, is graphene real? Does it actually work? It was pretty experimental. If we look today, I think there's no question that the technology works. Now the questions are more business model and business issues to get to adoption. And it is frustrating. You know it, and we know it, that there's an awful lot of work being done on graphene that's not public. It's also not patented. It's under trade secret. It's under NDA. So there's no way for anybody to actually know it. So it's a lot more pervasive than is obvious. As far as just sticking a little bit with business models, one way is to partner. That would be kind of like co-licensing or co-developing with joint venture and such as that. And the other route is, of course, creating devices yourself, kind of going up market and selling complete devices. And then we do have, the fee for service model or the foundry service model. What does the roadmap look like for Paragraf? Because you guys have achieved quite a lot. You've got a good sized team. You've got really solid science. What's the next 1 to 3 years look for you guys?
Yeah, it's a really good question. As a relatively new entrant into the biosensor marketplace, we're still working that out. Is the short answer. We're not particularly interested in just supplying graphene wafers or graphene dies. Our interest is really being further up the supply chain than that. But of course, it's a trade-off between, if we sold dies in volume, and as I think I've explained, we can achieve, certainly with the Series B investment that we're currently hoping to close, we can achieve some very significant numbers of graphene devices in short order, very soon. So we could actually just say, right, push it out into the marketplace and let people adopt it and do their own functionalization, do their own product development and get it out in as many places as possible. So that would see a rapid uptake of the technology, but for Paragraf, the value of each cell would be relatively small. And we're trying to work out whether that's the right approach or whether it's better to develop our own device and take that to market ourselves. And I think there'll be a hybrid model. And maybe we'll be making cartridges and selling cartridges through partners. But it's something we're working on, and really that's where the partnerships will help direct us. We'll be driven by commercial forces.
Yeah, that makes perfect sense. It doesn't have to be an either or. It can be a combination of those. But of course, then that brings you into bandwidth issues, right? You can only chase so many opportunities.
Absolutely. So if we're doing it all ourselves, then we're going to be, you don't have that much bandwidth to do lots of different diseases.
We do have a slightly technical question that I'll come to in just a second. Sticking with the business model questions just for one more. You mentioned, when you're talking to device makers, their response is, yes, I get a new proposition every single day about the most amazing technology, et cetera. Do you see a real technical competitor to these devices, or is it more you're just trying to get through all the noise?
So I think the difficulty with the medical world is that the medical world seems to think in disease terms. So they look at a specific disease and you get experts in a specific disease. So when you look at products that are competing in that space, it's usually, I don't see anything that really achieves what graphene can achieve. The speed is just phenomenal, and the ability to do a lab on a chip device is I think that combination is just unique. So I don't see anything competing with that at the moment. I think the existing technologies like PCR is being tuned. There's LAMP. I don't know if you've heard of LAMP, loop mediated amplification. That's a kind of newer version of PCR. It does the same job, new version of molecular testing. It's been around for a while, but the products are now gaining access to the marketplace, and much faster and simpler. So the existing technologies always get developed as need arises, and COVID has definitely prompted a massive influx of new products and players into the marketplace. But I don't see anything competing with graphene's overall performance. So the question is really getting that initial product out there and showing to the world that this really is quite awesome. And then I think it'll stem from there. There are, when you look at particular diseases, and we're focusing on at the moment looking at diseases where speed matters. When you look at those diseases, there are products that are really pushing the boundaries of what speed can be achieved. But I think it's always, when you talk about a disease, it's this combination of specificity, the ability to actually define which biomarkers will give you the best diagnosis, and how cost effective it is to do that product.
Excellent.
Because at the end of the day, most diseases have a defined cost point at which the diagnosis can be performed.
Right.
So cost is a huge issue.
Always on the per unit basis. I know that the device manufacturers, they will try to drive that as low as possible.
Yeah, and I think that's where, I do think that's where Paragraf makes a substantive difference, in that, without having to do the transfer process and therefore getting higher yields, we believe we can get a much better price point much more quickly.
And, this issue of educating the end user market, and in this case, device manufacturers or analytics companies, that's kind of why we had Laureline open up the conference yesterday morning, is kind of explain, what are they facing, because they're not materials specialists. And I think we shouldn't lose sight of the fact that graphene is a novel material. It's relatively new. Unless people are really material specialists, I don't think they appreciate what it can do. It sounds, I talked to somebody yesterday, they said it sounds magical because you're using so little of it, and it's both thermally conductive, transparent, electric, et cetera, et cetera. It has all these superlative properties, and it sounds too good to be true, but it's true.
Yeah.
Yeah, go ahead, please.
I was just going to say, everybody I've talked to, I certainly don't spend a lot of time talking about graphene, to be honest. I shouldn't say that in this venue, but I don't. I talk about the opportunities that it can realize in terms of speed, in terms of sample preparation, and those kind of facets of the things they're looking for. Yep. And that's what changes their mind. So I've had very positive receptions everywhere, but it is really a question of giving them the proof that the technology works.
Absolutely. On the technical question from one of the participants, the question, and I hope I do this justice, what is the spatial resolution for the chemical functionalization? Is it the same as the FET channel, the FET channel? And the question for Claire, do you perform chemical reactions directly on the electrode patterns?
Put it this way, we can make them smaller than they're useful. And the density of packing of the antibodies on your GFET does have an impact on the measurement. So we are tuning that. And as I think, as Elias explained, you also have to block other extraneous signals, other ionic fluids from the graphene surface itself. So you use blocking agents as well as capture bioreceptors. So it's that combination that has to be properly done. And when you're adhering when you're choosing your antibody, you need to make sure that you choose an antibody which binds only in one direction. Because some antibodies have multiple binding ducts, and then you get them lying down as opposed to standing up. So there are definitely games to be played there. But that's why we produce cells with lots of different sizes, so we can test that.
Interesting. Well, it sounds like you have lots of venues to pursue with the company as you go through this next stage of development. You have achieved quite a lot technologically, and we wish you every success with that. And hopefully a few of the companies listening in on today will reach out to you to talk about how they can work with you to develop some of these next generation devices, which are sorely needed. So with that, I want to thank you and thank Paragraf for being a member of the Graphene Council. I appreciate you sharing this information and keep us up to date on what's happening.
We will do. Thank you very much for the opportunity.
On behalf of the Graphene Council, I want to thank everybody for participating and for your interest in this sector. Clearly, graphene has a very important future in healthcare applications, whether it be for devices, medical sensing, diagnostics, or even in some of the infrastructure of gowns and devices and elastomer products, etc., that can be enhanced with graphene. So with that, I want to thank you very much. Thank you for your interest in the Graphene Council. If you have any questions, if you need any guidance, if you need information, anything to do with graphene or any of the companies that you saw in the past 2 days, please reach out to us, and thank you for your time and attention.